Is this why whirlpools form in the bathtub when you drain it? So whirlpools are going to form because you have fluid. Well, let's think about that. So my guess for why a whirlpool would form is because let's try and think about this logically. Let's open up Paint and let's think. And then we'll check our answer. As you can see, this is the stuff that gets me excited. Okay, you guys can see that. Also probably not link my stream. I don't think there's anything on there, but okay, so if we have a bathtub, and this is the initial state of the bathtub. We have water in the bathtub, and then what we're doing when we drain it is we just open up a thing here. And so what's going to happen is the fluid immediately right here is going to go down, which is going to cause, is it going to cause a pressure difference? So the flow is driven by gravity for this, and then hydrostatic pressure. So assuming that we okay, let's just assume that this is how it's set. Let's assume that it just drains like this. We'll even make it even. So assuming this is what happened, and then out here is also atmospheric pressure. So if we have atmospheric pressure here, and then atmospheric pressure here, then we're going to have a force down, and it's going to be driven by the hydrostatic pressure of this body at any. So my guess would be that when the fluid if we examine a fluid molecule here, it's going to move down, which is going to in turn make a fluid molecule here move this way, and a fluid molecule here move this way. And then we're going to have a fluid molecule here, because this is going to be a sink. So it's going to be if this is the drain, we're going to have fluid flow like this in all directions, and then up. So if you have fluid flow in all directions and then up, the fluid is probably going to cause a stress, and that's what's going to. Why do whirlpools form? My guess is that it causes a stress. My guess is that the currents are going to hit each other, and then this current, say, is going to influence the other current in a bathtub. The mechanics of a simple bathtub whirlpool are very similar to a tornado's vortex. Okay, if you've ever watched a whirlpool form in your bathtub or sink while draining the water, then you've witnessed the fundamentals of a tornado at work. A drain's whirlpool, also known as a vortex, forms because of the downdraft the drain creates in the body of water. The downward flow of the water into the drain begins to rotate, and as the rotation speeds up, a vortex forms. Why does the water start rotating? This is what we care about. Because this makes sense. I mean, if it starts to rotate, it's going to cause other things. This is going to cause other things to rotate around it, and so in turn, we're going to have a net acceleration acceleration of rotation until we get to the there are many explanations, but here's one way to think about it. Imagine yourself as a particle in the water, suddenly pulled down toward the suction that the drain creates. At first, you'd find yourself accelerating towards the drain. Then, quite literally, there's a twist. Because of your previous momentum and the number of other particles rushing toward the drain at the same time, chances are that you're going to be pushed off to one side of the point of suction when you arrive. That deflection sets you on a spiraling path into the point of suction, like a moth spiraling in toward a light. Once the spiral has started in one direction, it tends to influence all the other particles as they arrive. A very strong spiraling tendency is created. Eventually, there's enough spiraling energy to create a vortex. Vortices are obviously a common phenomenon. Not phenomena. After all, you see them in tubs and sinks all the time. Small dust devils sometimes form when winds flow over hot deserts. If you've ever lived in a desert, you see these things all the time. And wildfires have been known to produce climbing vortices of flame and ash called firewalls. I've actually always wanted to see one in person. Um, Scientists have even observed dust devils on Mars and spotted solar tornadoes whipping out. So yeah, so these streams are going to like bump into each other, and like if you have a stream like this way and then like a stream like that way, it's going to cause a transfer of momentum. So like this stream is going to be deflected slightly to the side. And so then that velocity vector now going to change like this, and then that's going to affect something else, and then we're going to do this thing. Okay, so that is why bathtub form vortices. That's pretty interesting though. That is pretty interesting. Oh my god, these things are epic. All right, Shiny Bree, you want another one? Okay. Okay, so we'll do what we were about to say. Let me pull up paint. Okay. Clear this. Dude, I'm gonna make a whole YouTube series for you guys. Okay? I'm gonna put all these together, and then you guys can go back and watch them. Remind me to do that. Pressure me to do that. Okay, so let's say you have a tank of water. Something like. And let's say that over here you have a piston applying a force 1. And then over here you have. Your drawing skills are unparalleled. Yeah, I'll mark whenever I do these. Here, let me write down the time in this so that it's easy to grab. I don't know why my stream markers aren't working. Okay, so let me make sure I have. Let me make sure I have this correctly. Or correct. Okay, so I mean I can't remember what it's called. Let me remember what this is called. Okay, so if a pressure is a force for an area. Okay? So what you can say is fluid pressure is identical for the same height. Okay? So if this has a cross-sectional area, let's say this is a a thing here. Or let's see how we want to do this. So we have two pistons. We're just going to draw it like this. And so this has an area of A1. This has an area of A2. Oh, wait. Backwards. Okay. So if force is equal to pressure times area, what does this mean for us? What does that mean for us? That means that since pressure is equal everywhere, so if we have a fluid here at this height, let's make our piston. Let's make our piston here. Okay, we have our fluid here at this height. That means that the pressure here is equal to the pressure here. So what we can do is say, because the pressures are equal, we can say that force, so there's some force over here, call it force 2. Okay? So we can say that force 2 over area 2 is equal to force 1 over area 1. Okay? So what does this mean? Let's say that A2, as shown in the drawing, is greater than A1. Okay? So then, what happens so what we'll see by that, if A2 is greater than A1, that means that the force on the larger face is smaller than the force on this face. So let's say that A2, for sake of argument, is 4, and A1 is 1. Don't worry about units. Okay? So that would mean that the force on 1, on face 1, is 1/4 of the force on A2. So if we apply a force like this on this face, then the force that we feel to compensate over here is going to be 4 times greater than the force we apply. I can't remember what this device is called, but it's a type of pump that takes, you like take the device and you push down the fluid and it goes around, and then you have a little hole that pushes up. And so if you have an area that's 10 times greater, then you can multiply your force by 10 times. So if you need a very, very strong force, you can do it using something like this. That's it. There it is, boys. I'll try and remember what it's called. It has to be liquid, yes. Because, well, could it be a gas? It has to be fluid. I don't think it has to be a liquid. No, lasers wouldn't work. Well, lasers have some interesting stuff too about their intensity per unit area and how much energy they can emit. I changed my scene off of monitor. Okay. Lasers can actually you can actually levitate objects with lasers. if the objects are sufficiently light and the laser that you have is sufficiently strong, you can have a levitating object with a laser.